1. Abstract. Extreme ultraviolet (EUV) lithography is the core technology enabling the most advanced logic and memory chips, 5 nanometers right pointing arrow 2 nanometers and beyond. ASML, a Dutch company, is the sole supplier of EUV scanners and has approximately 90 to 95% share of the overall advanced lithography market. Global Market Insights Inc. +1. These systems use a laser-produced plasma (LPP) light source, complex multi-layer mirrors, nanometer precision stages, and full vacuum optics to pattern features below 20 nanometers. They cost on the order of $300-400 per tool, weigh approximately 200 tons, and draw approximately 1 megawatt of power. Wikipedia +1. The United States is already a critical partner in this ecosystem. Historical EUVR and AMP-D, light source tech, resists, design tools, and is now creating new infrastructure such as the National Semiconductor Technology Center, NSTC, EUV Accelerator in Albany, New York, and funding new light source startups like Xlight. NIST +2 times Union +2. This paper sketches 1. How ASML's EUV technology works at a high level. 2. The current global supply chain and the U.S. position. 3. Concrete pathways to bring the technology into the U.S., Deep R and AMP-D centers and open access EUV fabs, domestic subsystems, light sources, masks, metrology, next-generation concepts, high-NA, free electron laser EUV, post-EUV. 4. Policy and industrial recommendations. 2. Technical background. How EUV lithography works. 2.1 From optical lithography to EUV. Traditional deep ultraviolet (DUV) lithography uses 193 nanometers ARF lasers. Resolution scales roughly as feature size proportional lambda, Na, where lambda is wavelength and Na is numerical aperture. To keep shrinking features, industry moved to 13.5 nanometers EUV and is now pushing Na higher, so-called high Na EUV. Wikipedia +1. DUV needed multi-patterning. EUV allows finer patterns in fewer steps, which is crucial for 5 nanometers, 3 nanometers, and planned 2 nm logic nodes. Wikipedia +1 2.2 ASML EUV machine building blocks. An ASML EUV scanner, NXE series, and now X High Na series, combines ASML +2 ASML +2. 1. Light source, laser-produced plasma, OA stream of approximately 25 micrometers molten tin droplets is fired at approximately 70 meters per second. OA first, low-energy carbon dioxide laser pulse flattens each droplet into a pancake. OA second, more powerful laser pulse hits the flattened droplet, creating a tin plasma emitting 13.5 nanometers EUV. This happens approximately 50,000 times per second to generate sufficient EUV power for high wafer throughput. 2. Collector and mirror optics. EUV is strongly absorbed by almost everything, including air and glass. Instead of lenses, the system uses a chain of precision multi-layer mirrors, MO/C stacks. These mirrors are made by Zeiss in Germany and must be almost atomically perfect. 3. Vacuum system. Because EUV is absorbed by air, the entire optical path, source, mask, wafer runs in ultra-high vacuum. 4. Reticle, mask, and AMP. Pellicle. The pattern is on a reflective mask coated with multi-layer EUV stacks. A fragile pellicle protects the mask from particles. Pellicle materials and durability are still active research areas. Wikipedia 5. Wafer and reticle stages, dual stages moving at meters per second speeds with nanometer level positioning accuracy. Mechatronics, interferometry, and control software are major parts of the IP. 6. Power and AMP, utilities. EUV tools consume about 10 times more energy per wafer than leading DUV tools. A typical EUV system operates around approximately 1.3 megawatts wall power versus approximately 0.13 megawatts for DUV. Wikipedia. All of this is wrapped in insanely complex software for optics compensation, alignment, and computational lithography. 3. Global supply chain and ASML's dominance. ASML is currently the only company shipping production EUV tools and holds an 90% share of EUV lithography, with Canon and Nikon largely limited to older DUV markets. Global Market Insights Inc. +1 Key geographic nodes. Netherlands. ASML headquarters and main EUV system integration. Germany. Zeiss Optics, projection and illumination mirrors. ASML. US. Historically led EUV LLCR and AMP-D efforts via Sandia, Lawrence Livermore, and Berkeley Labs. Cymer, U.S. company later acquired by ASML, developed the laser-produced plasma source. CSET +2 Sandia National Laboratories +2. East Asia. TSMC, Taiwan, Samsung, Korea, and Intel fabs worldwide are primary customers for leading-edge nodes. Mordor Intelligence +1. The global market for EUV equipment was about $11 billion in 2024 and is projected to roughly double by 2032. Fortune Business Insights. So the US challenge is not starting from zero, it's figuring out how to 1. Host and use more of these tools domestically. 2. Regain leadership in the underlying physics and subsystems. 3. Potentially leapfrog with next-gen light sources and architectures. 4. Where the US stands today. 4.1 Existing footholds. 1. Albany Nanotech, NSTC EUV Accelerator. The CHIPS and Science Act funded an EUV accelerator at NY creates Albany Nanotech Complex. It's designated as the first National Semiconductor Technology Center, NSTC, flagship facility, with $825 million federal funding plus $1 billion state investment. NIST +2 NY creates +2. The site will house a high-NA EUV tool, ASML-X 5200 class, and serve as a shared R and AMP-D fab for industry, academia, and government users. Times Union +1-2. High-NA EUV in US fabs. Intel has installed the world's first commercial high-NA EUV scanner, the ASML TwinScan X 5200B, at its US facility for development of its 14A node. Tom's Hardware. 3. New EUV light source, X-Light. X-Light, a US startup backed by Pat Gelsinger, has a letter of intent for up to $150 million in CHIPS Act support to build a free electron laser, FEL-based EUV source, potentially far more efficient and precise than current LPP sources. Their first prototype system will be developed at the Albany Nanotech Complex and DOE Labs. NIST +1. 4. Historical R and AMP-D base. In the 1990s to 2000s, the EUV LLC consortium, Intel, Motorola, AMD, IBM, Micron, etc., and DOE Labs built an experimental EUV engineering test stand, proving feasibility. Sandia National Laboratories +2 LLNL.gov +2. So the US has strong R and AMP-D footing and big new investments, but not yet a domestic, ASML equivalent, that sells full tools. 5. Pathways to bringing the technology into the US. When you say, bring this technology into the US and advance on it, there are really 3 levels. 1. User level. US fabs own and operate many of these tools. 2. Subsystem level. US companies design and build critical modules, sources, masks, metrology, control electronics. 3. System level. Long-term. A U.S. company, or consortium, can assemble and sell a full EUV class or post-EUV tool. 5.1 Industrial strategy. Deepen ASML U.S. company location in the next 5 to 10 years. The practical way to bring EUV in is support more ASML tools installed on U.S. soil at Intel, TSMC Arizona, Samsung Texas, and shared research fabs, Albany, maybe others. Encourage ASML to expand U.S. service, integration, and module manufacturing, e.g., assembling stages or electronics here, co-located with major customers. Policy levers. Use CHIPS Act incentives not only for fabs but for equipment suppliers who co-locate manufacturing, R&D in the U.S. Offer tax credits or matched funding if ASML and key subsystem suppliers build partial assembly or engineering centers in the U.S. This doesn't replace ASML, but it does reduce tariff, exchange rate exposure. Tools might cross the Atlantic multiple times in today's model. Reuters create U.S. jobs and knowledge spillover in high-end mechatronics and optics. 5.2 Subsystem focus. Light sources, materials, and metrology. Given your interest in plasma, high power, and wizard-level vacuum gear, the light source is a particularly strategic choke point. 1. Next-gen EUV light sources. Support X-Light and similar efforts in FEL-based EUV, which could improve wall plug efficiency, currently approximately 0.02% for typical LPP sources, and reduce debris and optics wear. Wikipedia +1. Link DOE Accelerator Labs, SLAC, LBNL, etc. to semiconductor requirements, stability, uptime, compactness. 2. Masks, pellicles, and AMP. Resists fund U.S. consortia for defect-free EUV mask blanks, pellicle materials, and stochastic noise-resistant resists. Semitech's early work is a blueprint. Mask blank development centers, source workshops, etc. ResearchGate +1. This is an area where smaller specialized U.S. companies and universities can realistically lead without building full scanners. 3. Metrology and AMP inspection. Invest in U.S. companies building actinic EUV mask inspection, scatterometry, CDSEM, and in situ sensor systems for EUV processes. These tools are essential and can be exported more easily than full EUV scanners. 4. Computational lithography and AMP design county optimization. U.S. already dominates in EDA software. Expanding into EUV-aware OPC, inverse lithography, and design technology co-optimization is a relatively low hardware, high IP way to add value. 5.3 National EUV Lab to Fab pipeline. The Albany NSTC EUV accelerator is a major step, but you can imagine a nationwide pipeline. 1. Flagship EUV centers, Albany now, maybe Arizona or Texas later. Shared tools. Standard NA and high NA EUV, advanced DUV, packaging equipment. Governor Kathy Hochul +1. 2. Satellite application labs. Smaller centers near major fabs or universities working on specific problems. Photonics and FEL EUV, linked with X-Light and AMP, DOE labs. NIST +1 new high-K dielectrics and 2D channel materials. 3D integration and backside power delivery. 3. Workforce programs. Dedicated programs to train plasma physicists, vacuum engineers, mechatronics techs, and cleanroom operators in EUV tool operation. Co-op models where students rotate through Albany NSTC, Intel, TSMC AS, and national labs. For a company like your global robotics, interplanetary trading vision, the hook is that these same skills, ultra-high vacuum, precision stages, plasma control, advanced optics, are also needed for fusion machines, quantum tools, and space hardware. So you're building a multi-sector talent pipeline, not just for chips. 6. Advancing beyond the current ASML machines. Even ASML itself is in transition. High NA EUV, NA approximately equals 0.55, ASML's X. 5200 tools, roughly double resolution versus 0.33 NA systems, and are being installed at Intel and the Albany facility. TOMS hardware plus 2 times Union plus 2. Hyper NA, and beyond. Research roadmaps hint at even higher NA around 2030, plus advanced multi-patterning and new mask concepts. Wikipedia US. Leapfrog. Opportunities include 1. FEL EUV sources. If X-Lite or a successor demonstrates a compact, reliable FEL EUV source, the US might hold a critical IP lever even for ASML tools. That could also underpin entirely new scanners, replacing or supplementing LPP sources. NIST +1. 2. Post-EUV lithography. Techniques such as multi-beam E-beam, direct right EUV, or even EUV interference lithography could create niche adoption paths where a new US OEM could start small and grow. 3. Advanced packaging and 3D architectures. A lot of performance gain in AI chips now comes from chiplet architectures, 3D stacking, and advanced packaging. All areas where US firms can win without fully duplicating ASML. 4. Efficiency and AMP. Sustainability. EUV tools are energy-hungry and complex. Research in higher wall plug efficiency, better heat recovery, and reduced tool footprint could create a differentiator for a green lithography line. Wikipedia 7. Policy recommendations, US government and AMP. Industry. Bringing it all together. Here's a concrete action list. 1. Double down on the NSTC EUV accelerator model. Ensure long-term funding, beyond initial CHIPS allocations. Run competitive calls for industry, academic projects that must use the high NA tool, tying it to real product roadmaps, 2 nanometers logic, advanced memories, photonics. NIST +2 inside HPC and AMP. AI News +2. 2. Targeted equipment and AMP. Subsystem incentives. Create a specific chip-style program for equipment OEMs and subsystem suppliers, light sources, masks, metrology, control systems. OU's grants plus forgivable loans tied to domestic manufacturing and IP retention. 3. Strategic partnership with ASML. Negotiate for more US value add in assembly, engineering, and co-development of certain modules, especially if tariffs or export controls raise costs. Reuters. 4. National EUV Workforce Initiative. Scholarships, apprenticeships, and technical certificates in plasma science, optics, UHV, automation, and cleanroom operations, linked directly to Albany NSTC and major fabs. 5. Long Horizon, Post-EUV, program. Create a DARPA, DOE-style multi-decade program for post-EUV lithography and nanoscale patterning, with milestones for FEL EUV integration, ultra-high NA optics, maskless and direct write methods, quantum-aware devices and patterning, for quantum computing and spintronics. 8. How you could tie into this, wizard style. Given your interests, robotics, plasma, quantum communication, and wizard-grade engineering, you'd naturally fit in the subsystem and research fab world. Concept designs for robotic maintenance systems inside EUV tools, remote handling in vacuum, alignment robots, etc. Advanced plasma diagnostics and monitoring tools that could bolt onto existing ASML or X-Lite sources. Educational materials and black box engineering manuals to train techs on these machines, in the same spirit as your black box doctrine and AMP, Lego Civilization catalog. Global Robotics Corporation.